First of all, I want to thank Francisco for organizing this conference. I know he faced special challenges in organizing the conference, and I want to congratulate him on a great talk. Congreso, I was thinking. Okay, so my talk is going to be about machine learning. So before we start, I want to make sure that everybody understands at least the basics of what machine learning systems do. So who in this room would be able to explain confidently how machine learning works? I want a show of hands. 1, 2. Okay, 2 people. So that's why I prepared some slides to give you the basics, because I assume that most people don't really understand how things work. Okay, so I'm going to be talking specifically about a type of machine learning which is called supervised machine learning, which is the idea that a machine can imitate a task usually performed by a human. In this case, the typical example is image recognition, where a human being will see this picture and then say, well, it's a cat. A machine learning system is going to be trained to do exactly the same thing, to see the image somehow. It's going to learn to identify cats and then come to the decision that the image is a cat. So how does this happen? The idea is that you have to train the system with hundreds of thousands of images. I'm just using this example, but this applies to text and to many other things. You have to train the system with lots and lots of images of cats and things that are not cats. So the system learns to understand which features of the pictures belong to cats and which features do not. So after you have decided on a data set, which is the examples that you use to train the system, you have to find some specific type of algorithm that you're going to use to train the system. So you can use decision trees, neural nets. I will talk about this a little bit in the next slide. And then once the system identifies certain features in the hundreds of thousands of images, it infers a certain function, a mathematical function, which takes you from a picture of a cat to the decision that you're seeing a cat. Okay, so the output can be either numerical or a label. You can just say it's a cat, or you can say there's a probability of so and so that this patient has a certain type of tumor, for example. And once the system has inferred a certain function, you have to evaluate whether the system is working correctly. So there's another set of images in this example, in which what happens is that you want to show different cats, different images of cats, and make sure that the system is getting the correct answer. Basically, that's how the system is trained. If it doesn't get the right answer, then you have to go back and fix, either check whether you have the right data set, or whether the parameters in the algorithm have to be fixed, and so on. Okay, so the most powerful algorithms are neural nets, which are represented here. You have a bunch of inputs, which are the x's, and then you have a bunch of layers in which the information is processed, and then you have the outputs over here. So you go from x to y. That's the function that the system is performing. And the thing is that these things have become extremely sophisticated. Some networks, some neural nets have over 100 layers. So each of these vertical balls is a layer, and the most powerful engines have over 100 layers. And the x's, in the case of powerful natural language processing systems like GPT-3, which has become quite famous, have over 175 billion parameters, American billion. So as you can imagine, these machine learning systems have become extremely complex, and that's why we call them nowadays black box algorithms. Because first of all, the algorithms that they use are extremely sophisticated. They use millions, billions of parameters in some cases. They have dozens of hidden layers, and they are not linear. In other words, it's not a linear function. There's lots of feedback in the functions, and they're also trained on massive data sets. So basically, what happens is that no human being can understand what's going on within a machine learning system of a certain power. So the thing is that once the system is exposed to the inputs, what the system sees in each of these inputs becomes sort of a mystery. So the system might focus on certain pixels of the image that human beings don't care for, or simply do not represent anything to a human being. And those patterns that the system starts finding maybe don't mean anything to a human being. So once you have this black box algorithm, once you have this powerful system, the thing is that there is a trade-off between how accurate the system can be and how explainable it is. In other words, how much can we understand the way it works. So NN is a neural network, and those are the most powerful algorithms currently being used. Or vector machines are also very common and very powerful. But then they're very low in terms of explainability. On the other hand, if you use something like a linear regression or a decision tree or something like that, those things are easier to understand, but they're not very exact. They're not very powerful in terms of the things that they can detect. So basically we have a trade-off between accuracy and ... What people call explainability, understandability, interpretability. It's not clear exactly what these words mean in the context of computer science or in the context of machine learning. But it's very important currently in the computer science, in the field of computer science, to find ways to make the systems explainable or understandable or interpretable. Why? Because there is a trust problem in machine learning. People don't trust decisions made by machines because they don't understand how they work. So there's one big challenge there to try to make people trust a little bit more these systems, especially when the decision is a very important one, such as a medical decision or an insurance or an admission to a school or access to housing or credit. And when the machines are the ones deciding those things, people want to know why they were denied credit or housing or any of these services. So that's one problem. The other problem is that some regulations, for example, in Europe, the GDPR, the General Data Protection Regulation in the European Union, requires that if a machine learning system is involved in a decision that affects the life of a person in a significant way, then there must be a way to transmit to the person the logic. That's what they say, the logic of the system, how the system reached that decision. So the goal is to understand what the system does, why it reaches certain decisions, and how it does such a thing. And that's the field of XAI. That's explainable artificial intelligence. So there are two main approaches to XAI. And I'm going to explain briefly the first one and tell you why it doesn't really work that well. And then the rest of the talk is going to be on the second type of approach, which is called proxy or surrogate models. Okay, so the main difference between these two methods is that post hoc methods want to explain a singular prediction. In other words, you have a prediction made by the machine, and then you want to understand why the machine reached that specific decision. While proxy models want to find a way to explain to people how the system in general works, not in this or that specific prediction, but rather in general. So let's take a look at a very easy to understand example of a post hoc method. This is a very well-known method called LIME. It was invented by a Brazilian researcher in University of Washington. So the idea is that you expose a machine to this image, and the machine says, well, there's a 54% chance that this is a frog. That's what the machine decides. So the question is, how did the machine reach that decision? So the method breaks the image into megapixels, of these little areas, and then it starts erasing parts of the image. So in this case, for example, it erased most of the image except the face of the frog, and then the probability went up to 0.85. In this one, you erase almost everything, and the machine doesn't know what it's looking at. And in this case, you erase part of the background, and the probability goes down a little bit. It's a little weird because there was definitely something in the background over here that was making the machine reach the decision that it was looking at a frog. So once you do this, you start to change the image, to erase parts of the image until you reach, you find out which megapixels are more relevant in reaching the decision that it is a frog. So here you have a weighted regression that tells you which factors were more important, and then that's how, once you have analyzed all the possibilities, you reach that these megapixels over here are the ones that were most relevant in the decision, and that's called an explanation. That explains why the machine reached the decision that there was a 54% chance that this was a frog. Okay, the other method is called heat maps or saliency maps, and it's a way of telling people which parts of an image were most important in the decision. It's basically the same idea, but with a different method. So this is an X-ray of a patient who had lung cancer. So the machine says, well, I forgot pneumonia. 85% chance that this is pneumonia. This is a 121 layer neural network. So once you have this, that's a very high chance that this person has pneumonia based on this X-ray. So what this system does, it tells you which areas of the image were most important in reaching the decision that this patient had pneumonia. So as you see, the machine focuses on this area in red, and the areas in blue are the least relevant. So that's why it's called a heat map, because it's a way to tell you exactly which areas are most relevant. Okay, so this looks great, like you're understanding a lot about how the machine reached a decision, but there are lots of problems with this method. The first thing is that these methods perform very poorly on robustness metrics. In other words, if you change the input slightly, the explanation is completely different of why the machine reached a certain output. Sometimes you just have to repeat the sampling process, and then you generate different explanations. So basically, the system is the explanations don't come out the same once you change the order in which you show the images, or once you make a very small change in a certain image. So that's a little weird that just by changing a few pixels, the explanation might come out completely different. They lack precision. So as you see as you saw in the previous image, if you look at this image in the area in red, has lots and lots of information. There's lots of things going on in this whole area. So what exactly is it that the machine saw in this specific area of the X-ray that made it reach the decision that this patient has pneumonia? It seems that we're still not at a point where you can tell exactly which specific pixel or which specific pixels were the ones responsible for that decision. Okay, and since the areas are so big, they have to be interpreted. And once you have to interpret an explanation of an image, then lots of things can happen. For example, you can have confirmation bias, or you can just try to move. I mean, if you see the red area, you will see in the red area what you want to see. That's basically how confirmation bias is going to affect your interpretation of that red area within the X-ray, for example. They're not generalizable, which is the most serious problem, I think, because different explanations of similar images have few things in common. So you want to explain how the machine detects that it's identifying frogs. But every time you look at the explanation of how it identified a frog, then you realize that the explanations have very little in common. And that means that you cannot really say that you have a general explanation of how this machine usually identifies frogs, because every time it's going to be a little different or very different. They can also be easily manipulated. So something called adversarial attacks is a way to alter an image in a way that a human cannot detect. So for example, you can just change a few pixels in the background, and then the prediction will be messed up, and the explanation will also be completely different just by changing a few pixels in the background. And another problem is that many explanations are completely incomprehensible to human beings. So let me show you an example. So this is a clean image of a dog. That's a collie, I think. And then these are altered images of alterations of this original image. As you see, this one is completely squeezed. The other ones are very slightly changed. And each of these columns is a different method to find explanations of why this is identified as a dog. So there are a few that somehow give you an idea that you're looking at a dog. I don't know if you can see these, but these are quite clearly dogs. But then this is just a blur. This is nothing. And some of these are nothing. I mean, you cannot, as a human, you cannot really understand exactly what's going on in many of these so-called explanations. So basically, you can tell maybe you can find a way to identify the pixels that the machine is looking at, but at a human level, you're left in the dark because these things are not telling you much about the whole process. So that's why I think there's a lot of hype around post-hoc interpretability methods, but I think that in terms of the degree of understanding they provide, they're quite weak. So during the rest of the talk, I want to explore the other kind of models, which are proxy or surrogate models, which are basically of two types. They're linear representations or they are decision trees. and there are exemplars, and there are some other types, but these are the two main types. And I want to answer two questions. I want to explore two questions. The first question is, what is the nature of those models? Because in science, people use models all the time. It's part of the business. And there's a lot of literature in the philosophy of science on models, on scientific models. So what I want to explore is whether you can think of those proxy models as idealizations, because it's not obvious that they correspond to the way that philosophers of science usually analyze these things. And the other question is, what kind of understanding of the target model do they provide? That's the second question that I want to explore. So let's get started. So what is a proxy model? But basically, a surrogate or proxy model is something simple like a decision tree. This is a decision tree in which you find a way to imitate or do something similar to what the primary machine learning system is doing and reaching some kind of explainable prediction. In other words, once you feed this system with some inputs, you're going to get some outputs which are not going to be as great, as precise as the original ones, but at least the system is going to be understandable in some way, and you will be able to see how the decision process worked. Okay, so the first thing that you have to keep in mind is that they are going to be false. They cannot be factive. This is a quote by Cynthia Bruden, who is a very well-known computer scientist. And she says, explanations must be wrong. They cannot have perfect fidelity with respect to the original model. If the explanation was completely faithful to what the original model computes, the explanation would equal the original model, and one would not need the original model in the first place, only the explanation. So there's an important fact here, which is that they have to be false. They have to be false representations of the original model. That's not unusual in science. Many models, especially so-called toy models, alter the original system so much that it's really impossible to say that there's a resemblance, a similarity between the two things. Okay, so since they are very coarse approximations of how the system behaves, you have to understand where you can use them and where you can't, what limitations they have. And in other words, you have to be very transparent with users so that people are not misled or understand things which are not there. So this is a quote by Mittelstadt, which is a professor at Oxford. He says, a user must know over which domain a model is reliable and accurate, where it breaks down and where its behavior is uncertain. If the recipient of a local approximation does not understand its limitations, at best it is not comprehensible, and at worst it is misleading. So proxy models are imprecise. They will never resemble the precision of the original model. So you have to really understand that you're not looking at the real thing. So if you go to a bank and the person in the bank tells you that your credit was rejected by the machine, the bank has to have some kind of proxy model to explain to you which factor perhaps was the most important in that decision. So maybe your income is not high enough, or maybe you have been rejected before for the same credit, or something like that. And that's going to be something that shows up in this surrogate model. Even though the original system that the bank used probably has taken into account hundreds of other variables which will not appear in this small surrogate model. So you're basically lying to the person in a sense, because you're not telling the person exactly why the bank rejected your loan application, but at the same time you're not lying entirely, because there's a very important factor which probably had a lot of weight in the decision. So that's what a surrogate model is. So the question is, if we look at the way that philosophers of science talk about ideal models, we're going to see that they don't really fit with any of the existent ways of approaching what an ideal model is. So I'm going to use this paper by Michael Weisberg, in which he presents 3 types of idealizations, which many people have written about this. So this is just an easy way to classify models. So the first type of model that people talk about are called Galilean models, which the most easier to understand example is an inclined plane. So the idea is that when you analyze this in a logic textbook, there's no friction on this plane. So if you had to take friction into account, the calculation would be incredibly difficult. So you're trying to find an idealized way of approaching the problem of inclined planes. And since this was a famous example by Galileo, that's why they're called Galilean idealizations. So they have certain features. For example, you introduce distortions and emissions on purpose, but the main purpose is to simplify calculation. That's the main objective of using this kind of ideal models. Because if you didn't, they would be either computationally or mathematically intractable, and we need to somehow get some initial understanding of a phenomenon if we want to advance science. Also, they're justified pragmatically because otherwise we would not be able to approach that aspect of reality. And a very important part is that we want to get rid of them. Once we have a better understanding of the mathematics or the computational complexity of the problem, then we will be able to get rid of them and find a de-idealized model. So this is a quote by Weisberg. He says, since the justification is pragmatic and tied to tractability, advances in computational power and mathematical techniques should lead the Galilean idealizer to de-idealize, removing distortion and adding back detail to her theories. Okay, so the question is whether we can think of proxy models in computer science, in machine learning, as this kind of idealization. And the answer is going to be no, for several reasons. First of all, they do share a pragmatic justification. In other words, we use proxy models because we need them. We need to explain to people how machine learning models work, and we have no option. We have to find a way to make them explainable. But the reason why they are simple models is not because we lack computational power or because we lack mathematical techniques. Because in fact, what happens is quite the opposite. We have very sophisticated and powerful computational techniques, and the problem is that we don't understand exactly how they are operating in the specific case of a machine learning system. So it's not that we lack the mathematics, it's that we don't understand how that mathematics is working within the machine. So the problem is different. It's not a problem of mathematical or computational intractability, but rather that once you make the mathematics and the computation work, you lose epistemic access to that system. And if that's true, then there is no future time at which an interpretative model or a proxy model will be de-idealized to match the original system. If it were to be de-idealized, it would become the very object it is meant to explain. In other words, it would become the machine learning model itself. So this way of understanding what an ideal model is doesn't seem to match very well with proxy models in machine learning. That's the conclusion. So let's move to the second type. The second type are called either Aristotelian idealizations or minimalist idealizations. So the idea is to build a model that includes only the minimal causal factors that give rise to a phenomenon. So you get rid of all the unnecessary details and you just keep whatever is absolutely necessary. So these accounts are usually considered factive. Most people who talk about minimalist idealizations think you have to remove things, but the factors that you're taking into account are the real factors. They're the true factors that make this phenomenon change or evolve or whatever. So for example, Frigg and Hartman describe them as the practice of stripping away all properties that we believe are not relevant to the problem at hand. Or Michael Strevens says that it's the omission of causal factors that are explanatorily irrelevant, and they might be relevant to the explanation of how an event occurred in a specific case, but they are irrelevant if we want to understand why the event occurred. So this is perhaps the most common way of understanding models. This is the most common way of understanding how scientists might want to simplify and find ways of dealing with reality just by getting rid of unnecessary details. So let's take a look and see if this works as a philosophical analysis of proxy models in machine learning. Okay, so this is an example of a minimalist idealization in science. Boyle's law makes the assumption that the particles in a gas are infinitely small, and once you have that assumption in place, then you don't have to take into account the way that they interact with each other. The only things that matter are pressure and volume, and then you have the curve that represents Boyle's law. So this is just an example. Okay, so what's going on in the case of proxy models? The idea is that you have to find the minimal elements that are going to come into play in the way that the machine learning system predicts. That's, if we find those elements, then we would have an accurate representation of what the machine learning system is doing. But what I argue is that it is impossible to think of a minimal model in these cases. Why? Because if you build a minimal model, you have to preserve some degree of facticity. That's an essential component for most people who think of minimal models. And if you want to do that, since we don't have access to how the system works internally, at least what you need is accurate functional generalizations. At least you need to find a way to match correctly the most important inputs to the relevant outputs. And what I want to argue is that those generalizations are epistemically unreliable, and therefore they're too weak to ground any causal claim about the system. This is perhaps the central argument of the paper. So why are they epistemically unreliable? The first problem is that not every machine learning system can be described in terms of functional regularities. Why not? Well, there are three conditions that any well-behaved function has to perform. The first one is that for every input x, there must be an output y. So if you give the machine an input, there has to be some decision. This condition is called existence, and the problem is that there might not be a distinct output for every single input that you give to the machine. That might happen. That has been proven to happen. The second problem is that it doesn't fulfill uniqueness. Uniqueness means that if you have two inputs, x, y, and x2, the output f of x1 and f of x2 is going to be the same if and only if they are the same input. And the problem is that once you have a data set to train a system, the data set might not be rich enough to fulfill this condition. Because if you run the algorithm in a different order, for example, the algorithm is going to reach a different decision. Even though you're showing the algorithm the same inputs, the same x's, but it turns out that it doesn't have the same y's. So there is not a unique answer for any pair of input in the system. And the last problem is that it's not a stable function. In other words, there might be, and there usually is, a lot of noise in the data, and that the function is going to be unstable because of that noise. So this is a very technical objection about what might happen. This happens in some cases that the system does not have a well-behaved function, but there are some other cases in which the functions are okay. So even if the system is well-behaved, this is a very subtle problem. The problem is that once you have a very complex function working and it doesn't have the previous problem, there's something called the model identifiability problem, which is explained by Goodfellow in these terms. It says, a model is said to be identifiable if a sufficiently large training set can rule out all but one setting of the model's parameters. Models with latent variables, in other words, variables within the deep layers of the machine, are often not identifiable because we can obtain equivalent models by exchanging latent variables with each other. So the idea is that since you have a black box, within the black box, you can have there's a certain function that was inferred by the system, but you can change parameters within the black box and create a different function. And from the outside, it's going to be doing exactly the same thing. In other words, in functional terms, you will not notice any difference, but internally, the model that is inside the box is going to be entirely different because you can switch the variables and you will never find out. So the question is, which model are we trying to explain with these functional regularities? If you can have, in some cases, an infinite number of models inside the black box, which one are you explaining? Which one are you trying to, what is your explanandum in this specific case? So what I argue is that a functional law-like generalization cannot identify unique models. In a sense, a functional explanation would be an explanans in search of an explanandum because we don't know exactly which is the model, which might be, which the system is performing. So it's a very strange situation which is not resembled in the physical world, I think, in which you can have an infinite combination of different variables, and each of those combinations is a different explanandum, a different thing that you have to explain. And this is another important problem. The way that machine learning models work is that they find very small correlations in the data. So correlations between certain pixels, for example, and the result they want, which is a cat, and they start finding those very subtle correlations that human beings do not detect. And since they are so fragile, there's such weak statistical regularities between inputs and outputs. Sometimes there are going to be lots of noise, lots of correlations that are simply false correlations, spurious correlations, which are not capturing really a causal relation between features in the images, for example, and the results. So you're basically finding out that lots of information in your input is not really causally correlated with the information you're trying to obtain, and the machine learning system doesn't distinguish between things that are genuinely causal and things that are not genuinely causal, and you might end up with a false image of how the world works. So, sorry, this is something else. So there's always a chance that a functional explanation will be overfitted. In other words, the system has been trained. It's great with the original training system. It finds the right answers for that training system, but since it has focused only on certain features of that training system, those are not features that are really causally important in finding the right answer. So if that is the case, then the model will lack epistemic value because it's not going to tell you anything about the real world, or when it's used, for example, in scientific research. So that's I mean, functional. The conclusion is that functional generalizations are too weak to be the basis for the construction of minimal ideal models. That's the point I wanted to reach. Finally, the last element in Weisberg's classification of models is what he calls the multiple models idealization. So he says the practice, what's that? It's the practice of building multiple related but incompatible models. So you construct many different models of the same piece of reality. But each of them makes a distinct claim about the nature and causal structure that gives rise to a phenomenon. So why do people do this? Because each model has a specific property that is desirable for specific researchers. So some people will prefer a more accurate model, a more precise model, a more general one, a more simple one, and it depends a lot on what individual researchers want from their models. That's basically the reason why you have a bunch of different models for different purposes. And this is very common also in science, where maybe engineers will create a model for a phenomenon, and then physicists will create a very different model for the same piece of reality because they pursue different goals. And the reason why they are incompatible is because they are based on different epistemic values. And which model you choose is going to be based on your individual interest. Okay, so is this a good way to think of the proxy models we use in machine learning? Well, again, this idea shares the pragmatic nature of multiple models idealization, because we want to use these models for a certain purpose. However, the goals that we pursue with proxy models are very different, because we know that the proxy model is not going to be accurate or realist, or you cannot generalize it. It's going to lack precision. All of those things have been sacrificed from the beginning. So you're not building models because you want them to be more accurate, or you want them to be any of these things that are the goals that scientists pursue, because you know that you're not going to reach any of them. You want to make the most simple thing that is usable by regular people when they have to face this machine learning decision. And of course, the target model, in other words, the machine learning model, is always going to be more accurate, more general, more precise than the best proxy model. So what the view that I want to defend here is that we have to think of proxy models in a different way, not as some sort of idealization, but rather as what several authors have called epistemic tools. So Evelyn Fox Keller, Boone and Canutila, and some other authors, Wendy Parker is another one, have approached the idea that models have to be used as a hammer or as any other tool, but as a tool to learn, as a tool to understand. So Wendy Parker, for example, called this the adequacy for purpose view of models. She says, on this view, model quality is to be assessed relative to a purpose. Model evaluation seeks to learn whether a model is adequate or fit for particular purposes. Such a view can be contrasted with one in which model quality is just a matter of how accurately and completely a model represents a target, where the ideal limit is a perfect and complete representation. So, how much time do you have left? 4 minutes. Oh, okay. Okay, so if we think of models, of proxy models in this way, the next question is, what kind of understanding do they provide? What kind of understanding do we reach with these things? And within the computer science community, usually the word that is most commonly used is interpretability. We want to explain or present in understandable terms to a human what the machine is doing. Or it is a degree to which an observer can understand the cause of a decision. So people want to make machine learning systems understandable, but that's where the philosophers come in to try to figure out what understandability might mean, what making understandable something is exactly. And that's basically what I want to answer in this last part of the talk. So one might think that post hoc interpretations, the ones that we saw in the beginning with the dog and the X-rays, provide answers to why questions. Why did the machine classify this input as belonging to that class? And perhaps the understanding that proxy models provide is more akin to how questions about the general functioning and architecture of the system. But I think that even if we think of post hoc interpretations in this way as answers to why questions, we're not going to go very far. And the reason is that if you explore the concept of understanding why, it seems that to understand why something happens, there has to be some sort of counterfactual reasoning involved. So for example, Canutila says, understanding of the possible is a way to understand why the actual emerged and how it functions. The question is whether these post hoc interpretations with the frog and the X-ray and so on have the ability to help you think counterfactually. And the answer is that they don't. They seem to be a form of counterfactual reasoning because you obscure a part of the image and see what happens and so on, but they don't really provide counterfactual understanding. Why not? Because what they're doing is basically tinkering with the input, making changes in the input, and users can only establish a piecemeal correlation that cannot be generalized in any obvious way. This is why I said that generalization is one of the most important things that this kind of interpretations lack. You can only see why the image found an explanation in this specific case, but not in general. And the main reason that I think that prevents users from having genuine counterfactual reasoning in the case of post hoc interpretation is that they don't have theoretical information about the workings of the system. In other words, they lack objectual understanding. So if you just have these little games where you see what happened in this specific case, but then that doesn't work again in the next picture, well, you don't have any sort of real counterfactual understanding because you don't know exactly what the system is doing. In other words, you lack objectual understanding. Sullivan, for example, in a very quoted paper that just came out, She argues that post hoc methods can provide understanding if there is adequate scientific and empirical evidence supporting the link connecting the model to the target phenomenon. In other words, you need theoretical knowledge about what the system is doing, how it's being employed, if you want to get some sort of sense of why the system changes its decisions in different moments. Therefore, it is doubtful that post hoc methods provide any sort of valuable understanding of machine learning systems. So the final question is whether proxy models provide objectual understanding. And here we have a better chance of obtaining some sense of understanding of the system, because if you look at the system as a whole, in a sense you understand which testing samples it has, what theoretical knowledge went into training and selecting the way it was going to work. There are lots of criteria around the model that can be incorporated into your understanding of what the system is doing. You're not looking at a single prediction, but rather at the system as a whole. And that includes how things fit, understanding how things fit together in the original model. How the selection of the data set had to do with the kind of predictions you were looking for. And the other thing is that they're definitely not non-factive. So this is a sort of, if proxy models provide understanding, it has to be non-factive understanding, because they are definitely not representing, not similar, not connected in a causal way to the original system, but they're showing you at least a global way of understanding what's going on within the system. Okay, so just to conclude, I have argued that post hoc explanations are unreliable, that these models do not fit easily into any category of idealizations in the philosophy of science, that proxy models provide non-factive objectual understanding, and that understanding cannot be reduced to functional explanations based on inputs and outputs. Thank you.
Thanks for the very interesting talk. I mean, this is very connected to some of the things that we are studying burden on connection with scientific explanations and understanding. So I had a couple of quick questions. So one has to do with the connection between proxy model as idealizations and fictional models. So where you think that this direction of giving up factivity actually suggests that when we're thinking about the nature of proxy models, we should think as this as fictional models. Mm-hmm. And you might, if you like this view, then you shouldn't be worried about realism. You can still treat them as epistemic tools, but then you might think this gives us a better understanding of how these models are supposed to work. And the second quick question is a curiosity that has to do with counterfactual reasoning involved. So I don't work in the area, so maybe you know that. Is where you think there are some connection with this way of understanding proxy models and interventionist models that has to do, for example, in science, where when you think of interventionism and you apply interventionist model, then this gives you a really nice way of thinking about counterfactual reasoning. Mm-hmm. You wiggle a variable, you wiggle another, you get this kind of patterns, counterfactual dependencies, and then you can think of understanding. I mean, this is one reason why you might like interventionist models and counterfactual reasoning is because it's very epistemically accessible for humans, right? Because it's really about let's intervene on the variables and see what's going on, right? So I was wondering whether you have any thoughts of potential application to both fictionalism on the one hand, about the nature of these models, and then counterfactual reasoning in connection to this kind of interventionist approach, right?
Okay, let me start with the second question. I think when you think of intervention, you have to think that the variables that you're intervening are variables that you can understand, that you can that have values that you can manipulate, increase, decrease, and so on. And then see what happens to the entire system. And so you adjust different variables and see what happens. That's how you intervene in a system and think counterfactually. What would happen if I do this? But in the case of machine learning, you don't really know what the variables are. So you just expose the machine to some inputs, and the variables that are going to be taken by the system as important are known to you. And since they are unknown to you, you cannot manipulate them. And if you take into account that you can be talking about billions of training samples that you're using, it's very difficult to say, well, I'm going to only use red images or only circular images, because then your system is not going to be very powerful at all. So you need to use the widest variety of samples that you can. And it's very difficult to think of intervening in how you choose the samples to find a different output. The other thing is that running these things is very expensive and very difficult, and I mean, not very difficult, but very expensive. So every manipulation requires a lot of work. And even if you try to manipulate the data set that you have originally, it's going to be a huge effort trying to figure out what is the thing you want to change in the data set. So it's not a very, I don't think it can be used in that way. I don't think you can use this kind of manipulation within machine learning. Now, the first question was about fiction models. The terminology in the literature on models is a little bit tricky, because when people talk about fictional models sometimes, I mean, they mean different things by that. So one way of thinking of fictional models is what some people call toy models, which is models that don't really have a representational function. So in some physics textbooks, you might find some image that tries to explain to you how thermodynamics works, without really making any connection to any real system, but rather showing you how variables might change and so on. So that's a little model, a little toy model that doesn't have that connection. So in that sense, it's completely fictional. It's an invented model that doesn't have any kind of representational function. But once you try to connect your model to some real life system, some real system, then the question is, what kind of relation exists between the model and the system? And then it becomes a little bit difficult to continue talking about fictional models, because fictions seem to imply invented things that do not exist. And if your purpose is to represent in some way the original system, then the fictional part becomes a little bit tricky. So we would have to define a little bit better what a fictional model is, I think, to do that.
Yeah, I think that's correct. I mean, a lot of fictions, they do have elements that tend to represent or like preserve, like the accuracy, or like they're real more like think of a fictional story, like Harry Potter or whatever. Right? Yeah, they're like invented parts, but they're also like parts that are real and are preserved as such. And I was thinking that on your preferred view of like if we care about these epistemic kind of benefits that this model are supposed to bring us, right? Maybe like in that particular case, it's acceptable that certain parts are invented, even though like it would seem to me that it's still compatible with your approach, but some other parts of the model are indeed like latch onto reality, so you still have some sort of aptness of the model, which is not the aptness that maybe the kind of like scientific models tend to aim, because we want to represent truthfully, but you are already giving non-factivity, right? So for you, that is not a sort of constraint that you should be pressured to say, yeah, sure, they're invented, but like they give us the sort of understanding that we want, and they work for epistemic reasons, so they're accessible. So they're fictional in a certain sense. So yeah, I mean, but I think I agree with you that it really depends on how we think of fictionalism at the end of the day. So.
Right.
Thanks.
Thank you.
Very helpful to me. Can I press you a bit on the inutility of the initial approach? The heat
Yeah.
And you said something there that I thought that's a bit odd. You said they're not robust because visually similar images won't necessarily give you similar outputs. And I thought that that's just what we expect. The machine is seeing different things than we see, and what probing will do is show us which aspects of the image are triggering it, and same response might come to things that don't look visually similar to us, but we might be able to see what the similarity is. It's just not the most obvious visual similarity for us. But then at the end you seem to suggest that that really wasn't going to work. Whatever you think you can find is never going to generalize from one sample to another. But it wasn't obvious why that should be so. I mean, this is just an empirical fact to do with the overfitting. I mean, why is it that we can't detect what similarities in the image are doing the work?
Okay. So I think robustness has to do with whether your functional generalization is robust. That's how I understand the robustness problem here. So if you have the same inputs, you should get the same outputs in the machine, in the system. But the way that machine learning systems are trained is that you have there's hundreds of thousands or millions of different inputs. And the order in which you train the system is randomly determined. There's a way to make it random. And you train it in one way, and then you get a certain result. But when you train the system in a different order, with a different random mechanism, the resulting model is going to be different, even though the initial data is the same. So that means that in its present state, they're not very reliable, because you cannot trust that once you give the machine a certain amount of data, it's always going to give you the same type of predictions. So that's why the functional generalization, I think, is not very trustworthy. Now, how does that connect to the images of the X-rays and all this? What happens? One problem is that you might have the X-rays of two people with pneumonia, very similar cases of pneumonia. But just the fact that they're slightly different might make the explanations completely different as well. So maybe when you look at the two X-rays and you look at the heat maps, there's a big red blob on the lower right corner of the lungs. But maybe what is inside that red area might be entirely different in one case and in the other case. And we don't know. We can't know because at least currently, the XAI methods that we have are not precise enough to tell you exactly which pixels are the ones that give you that information. But even if that is the case, maybe you change the lighting of the X-ray slightly, and then the explanation might change entirely. So it's very fragile. They're very easy to manipulate if you want to manipulate them, but they're also very fragile to any change in the way that the image is presented to the machine as well. So currently, if you have a specific prediction, I wouldn't trust. It wouldn't be very helpful in my understanding of what the machine did to look at this big. there's a lot of information in that area. That's my point. So I answered two different questions, but I don't know which one your question wasn't originally. Okay.
So we have three questions. Tony, then Federico, and then Cynthia.
You've raised a very important problem and present, also with ethical consequences because of the biases that these technological systems may use.
Mm-hmm.
Sure, you know that we all know the example of the classifier that excluded black women from the set of women.
Mm-hmm.
So there's a real question here. But then you discuss what seems to go against what the problem you raised. You discuss this notion of surrogate model, which is what is the very possibility of them is what is under question.
Mm-hmm.
The problem that you raised is that we have systems and we don't understand how they reach the decisions. But then in the second part of the talk, you discuss how to understand these surrogate models that try to clarify what's going on. But this is the real problem. How we can find a structure of what's so massive and so complex in terms of the layers. And in this respect, I would like to add a further constraint related to interpretability. Because the models that you are, the surrogate models, the models of the artificial system, of the neural network, whatever, are not just, they don't have just to be a model of the system, but also a model of how we do, of how we take it to be a good explanation of the task.
Of the what?
Of the task. Of the
Yeah.
Remember that artificial intelligence started as an effort to understand cognition, human cognition. So the bottom line is that we want to make sense of the model. If the model says that, from the pneumonia example, that the pixel in the upper left corner is critical, yeah? There's some information there. This is not going to be a good model for us, because for us this makes no sense. So there is sort of objection, but also an invitation to go deeper into the difficulty of devising or to constructing these surrogate models. There are no algorithm for that.
No.
So I think this is important to
Yeah.
say more on how the field.
I think it depends.
This pressure
Hmm.
has an important role.
I think it depends a lot on which field or which task you're trying to understand, because in the case of, for example, a bank loan, it might be easier to find a proxy model that gives you the main elements that come into play when you make a decision about money. In the case of visual detection, I think it's a huge challenge, and I think it's very difficult to find anything that might be generalized about image recognition. I think image recognition is one of those things that is bound to be incomprehensible for a very long time. Other than these heat maps and these the line method, which gives you understanding of one image. But otherwise, I think it's a very huge challenge in the case of visual recognition. I agree. But in the other cases, which are more critical perhaps to common life, to the life people who apply for loans, who apply for housing, who apply for healthcare, then maybe in those cases it's easier to find proxy models that will fulfill the European requirement on the one hand, and on the other hand might make people feel like they can trust what the machine did to some degree at least.
Okay, we have 2 short questions.
Okay, thanks, Andrés, for the great talk. That was very persuasive. I have a very simple-minded thought about the motivation behind the very project of explainable AI.
Mm-hmm.
I mean, on one hand, you have like the scientific motivation to understand what is going on inside the black box. But on the other hand, you have the user requirement of. I'm thinking, for instance, of the European regulations you mentioned, of like finding answers that people might feel comfortable with regarding how decisions are reached. And it seems to me that maybe what might make people comfortable or feel less unsettled by these systems is just something that may not be really there. I mean, maybe what would make people feel comfortable is nothing short of human-like reasoning and understanding, and they won't get that from any model of how these systems work. So say that I go to the doctor and the doctor tells me that I need to go into surgery tomorrow, and the only thing I got from the doctor was that, oh, I'm focusing on these pixels. Even if that were reliable and robust and precise, well, but what I need is to have the sense that this person is weighing all the alternatives and weighing all the considerations and is aware to the inconvenience that goes into undergoing surgery and so on. But that's how human reasoning works. And yeah, I mean, that's the single-minded thought. Maybe we won't get what would make people feel comfortable about this.
Yeah, actually, in medical contexts, there's a huge problem because even if you show that a machine learning system is more reliable than what a doctor will tell you, the way that doctors interpret X-rays, for example, and that's the point where we are right now. They're equally reliable, but very soon the machines are going to be more reliable than doctors. But when people are asked about why they don't trust the machines, then they say, well, the way the doctor talks to me about my disease and is kind of comforting, and there's a more human relation. Those are things that have nothing to do with how reliable the information is. And you're right. I mean, this project of XAI can only go so far in creating trust. There are going to be other elements that have to come into play which are not internal to the systems, but the way that information is presented that will have to be also included, I think. But yeah, that's a big challenge. We're all human beings.
Okay, short question because there's coffee waiting for us.
This might be a version of David's question. So if I understood correctly, so the big portion of the argument was these proxy models are not robust enough to provide. Not the proxy models, the machine learning system. Yeah, to provide for the expert.
Okay, so the lack of robustness is in the original model, in the original machine learning system. That system is not very robust because it might be changing the predictions all the time with very small changes. So the proxy models are not unreliable because we are making them ourselves in a very simple and understandable way. They're never going to be as precise and as accurate as the original models, but somehow we have control over what we're doing. That's the thing. But how useful they are is going to depend on the task that you put them to. Yeah.
Okay, thank you very much.
Thank you.